Okay, thanks, Amir, and thank you everyone for listening. In fact, with Amir, we had a few different topics that we wanted to cover, and we didn't know which one to pick for this conversation. I mean, the field is moving so fast, and there are so many interesting things. But at the end of the day, a few days ago, I decided that fine-tuning probably is one of the most pressing one. I know that Suhas, if I pronounce his name correctly, was also talking about this. This is a slightly different angle. So there will be a little bit of overlap, but mostly different type of material. So with that, let's just start about talking about fine-tuning large language models. And the base idea is that how do you create customized models that are specific for your domain or your problem? Okay. Let's just start with a very quick history of the development in large language models. So this is, in fact, a tree that I borrowed from. I leave all of the links in the slides, so you can later take a look at them. So these are different types of language models that have been developed in deep learning. So we don't go before deep learning. Of course, there are like other stuff too, but in the modern deep learning era, these are mostly the kind of development that we had. So in particular, we're going to take a look at only the transformer-based models. And if we narrow our vision only to those models, then we will see these kind of development from 2018. So the subtree that you see on the most right is as you can see, it has many leaves. That's the decoder-only subproblem, and these problems are problems that these models and tasks are the autoregressive tasks. Basically, the pre-training of these models is through next token prediction. Mostly, there are variations of it, but it's mostly like that. And it's essentially started with GPT. So OpenAI started that approach. There's also the other parallel approach in encoder-decoder. Probably you have seen FLAN family of models from Google. Those work very well too for some problems. But I can say with high confidence that the majority of the development, at least in the past 2 years, has been on this right subtree. And you can see all like BART, GPT-4, Llama, blah blah. And so these models are mostly trained through self-supervised training. So either through masked language modeling, MLM, as Hugging Face call it, or causal language modeling. Again, CLM, as Hugging Face call it. I know that Amir doesn't believe that these are actual causal models. We have a little bit of disagreement over there with Amir, but at least on the terminology, we call them causal language models. So these are the models that basically get some context and create some responses for that context. In that sense, we call them causal. So this is a little bit of history of the development in this domain. And as you can see, it's very hot, a lot of development. So how does the pre-training is done? It's, as I said, it's a pretty simple pre-training. And the idea is pre-training is a autoregressive type of training. And essentially, you do next token prediction. The good thing about this is that this is a very simple setup. First of all, simplicity is really important. As you can see, like Python language is not necessarily the best programming language, but since it's simple, it has like flying over all of the other languages right now. So it's a simple setup. That's the first thing that is important for it. More importantly, this allows you to train on any kind of text. Because if you think about it, language, for example, as we have an example here, the chicken walked across, and then you have to fill in the rest of it, is one example from language. But you can do it for other things too. You can do code completion. You can do even tabular data completion. You can do completion for any kind of data that is tokenizable. And we learned in the past few years, for example, most recently by the Cosmos paper from Microsoft, that pretty much everything can be tokenized. So this is a very general purpose kind of pre-training that you can go over it and just train. And you can see that in that setting, pretty much the whole internet is your playground. That is tremendously important because, you know, these large language models, or in fact, in general, deep learning models, they get to good results only at a scale. So this is great. Also, the task, there's something very interesting about the task. Although the setup of the task is simple, the task itself is not that simple. And it means that it pushes the model to learn very interesting patterns. For example, if I give 2 plus 2 is equal to and ask for the next token, as we probably has been done many times in the data from the internet, the model should kind of understand how the mathematics works. And if you say that the president of the US in 1983 was, what is the next token? The model should know history. So these are just two examples. You can extrapolate from this. These models have to learn a lot to be able to do this autoregressive task very well. So this is about the pre-training. So when you do the pre-training and when you're done with the large language models that you have trained, the next, you're not done, in fact. The foundational model are trained in large data in, for example, in this case, in this autoregressive fashion. But in this raw form, they're not that usable. They are versatile in a sense that they adapt to a new task. If you basically put a new task on top of these language models, they can be trained very quickly. You can also do few-shot learning on top of them. For example, context learning, in a sense that you have seen before. You give some context and you show some examples to the model, and then the model follows that. But in the raw form, they do not follow instructions and they don't answer questions. So the knowledge is stored in them, but one needs to extract the knowledge. A very nice diagram of this that probably some of you have seen is this monster of a language that has like all these crazy things going on about it. And then you do it and you do some supervised fine-tuning on top of it, and it gets a little bit better. And then you do finally some reinforcement learning with human feedback, and then this smiley, cute guy comes out of it. So the way that I like to see, I like to think about it is that you have this rock that in its original form, it's not that shiny, it's not that beautiful, but you can cut it. You can cut it, and after you do a lot of cutting and you make it clean and shiny, then it turns into that diamond that glows, and like it's very beautiful, right? So the same idea here. It's not necessarily injection of new knowledge, but it's extraction of the knowledge in these language models that is done through fine-tuning. And there are two main methods of fine-tuning. There's supervised fine-tuning, and there's reinforcement learning with human feedback fine-tuning. So RLHF. So yeah, as Amir mentioned, it's essentially you want to inject a good kind of bias to the models. Okay, so let's quickly think about the supervised fine-tuning. The supervised fine-tuning works like this. You first create a diverse set of prompt data set compatible with your task. Maybe you care about financial stuff. Then your prompts probably are focusing in financial material. sample the prompts data set, and then show these prompts to the labelers. The labelers go ahead and complete those prompts with the query appropriate for those tasks, and then this will be this will create for you these pairs of query responses. And then you feed these into the model, and you fine-tune the model. You still do the fine-tuning in the sense of autoregressive. But now in this specific format that you have query and responses, and it's a lot nicer than just crawling the internet. So it's kind of focused the model into a specific type of interaction. That's supervised fine-tuning in a nutshell. There are many things about that. I will explain a few of them later. For example, there is the question of efficiency and different types of training. For example, heft, parameter efficient fine-tuning, and those kind of things. There's a lot going on here. The other type that is quite different than the previous type is when you do reinforcement learning to fine-tune your language. And there are also several different types of reinforcement fine-tuning. For example, if you're familiar with Anthropic constitutional paper, they use other models to do reinforcement learning. So reinforcement learning with human feedback, human is not necessary in this setup. You can sometimes replace it with another AI. You can also replace it with some specific type of data. But the simplest setup that we have is the RLHF. So how does the RLHF works? The RLHF works like this. You show some, you create the responses again for your specific domain. And sometimes if you're OpenAI, you want to serve everyone, so you don't specify it, you just try to create a very diverse set of prompts. And then you expose these prompts to your model, and you get back some responses from the model. Then you show these responses together with the question to labelers, and the labelers just now rank these responses. So they say that, for example, the answer, like the question can be, explain the moon landing to a 6-year-old. And then there are 4 different answers that are created from the model, and the labeler comes in and says that answer D is the best, and then they answer C, and then A and B are more or less at the same level. So the way that the data is labeled is through this ranking mechanism. Then the ranking mechanism is used to create a reward model. The reward model, in general, what it says is that it can look at a response, and based on the examples that it has seen before from the labelers, it can identify what responses are better and what responses are worse. What you do finally is that now that you have trained and have a reward model, you apply that reward model through a reinforcement learning to your base model. Basically, the base model creates a text, and the reward model says that, oh, that was a bad answer, don't do that. This was a good answer, keep doing that, so on and so forth. So that's in a nutshell how the training here works. There's a lot here, though. Like this, one of the reasons that RLHF has not flied as much as supervised fine-tuning is that, in fact, this setup is pretty complex. I think this slides probably is the most comprehensive slides about RLHF. It's from Colossal AI. These guys are the UC Berkeley reinforcement learning team. They also work on other domains of machine learning, but one of their main focuses is reinforcement learning. So this is pretty much what RLHF is in a nutshell. Again, there's a lot to talk about here, so I'm not going to go into the detail of that. If you guys are interested, we can talk about them later. Also, I'm going to do a little bit of marketing for my own course here. So I'm creating a course in RLHF that it's free on YouTube. You can go ahead and take a look at it. And I will explain pretty much all of the pieces here. In fact, that course is based on this diagram from Clausalega. So that's that. Before I continue, let me show you in real time how the supervised fine-tuning changes the behavior of the model. If you have like a base model, let's say that it's a GPT or a llama or opt from Facebook, or I don't know, there are many of them. You saw the tree. And the idea is that how does the fine-tuning change the behavior of the model? And let me, in fact, show you a quick demo of that before I continue to the last few slides. So this is a fine-tuning that I did myself with some of the data that me and my colleague have collected. It's an extension on top of alpaca data from Stanford. What we do is that we get the llama model. This one is one of the smaller models, llama's 7 billion parameter from Facebook. And then we fine-tune it. This is supervised fine-tuning. We are in the process of completing the RLHF, but this one is the first stage, which is the supervised fine-tuning. These are a bunch of questions that I have here just as a way to show how the model changes behavior after fine-tuning. Feel free to shoot questions if you have for the model. I can do it in the live demo here. But let's take a look at a few examples of running it in live. So this is the base model. And the question is, what are the differences between dogs and cats? And the answer is dogs and cats are both domestic animal. Good. They are both four-legged. That's good. They both have fur. Sure. You see, this is not bad. First of all, there's a bunch of other things here that I like. This is next word prediction, right? It has behavior that is not necessarily desirable. Secondly, and more importantly, it didn't really answer my question that I asked, what are the differences between dogs and cats? Good that it came up with some of the similarities, but it didn't really answer my question. Now, this is the fine-tuned version of the same model, fine-tuned on a modest size fine-tuning data set. And then it says dogs and cats are both popular pets, but they have distinct personalities and behavior. Dogs are often more energetic and outgoing, while cats are more independent and aloof. Dogs typically need more exercise and attention than cats, while cats are blah, blah, blah. So you can see that it's the same model, but when we do fine-tuning, it behaves the way that we expect. And that's the main source of the huge success of ChatGPT and GPT-4, in fact, because they found a way to tune these models in a format that is really usable now. Let's take a look at a few more examples, and then I'm not gonna bore you with more. Let's see. Generally, you can see that the fine-tuned model works a lot better. I want to. Oh, but that's a spoiler. I have a good example, but I'm afraid that it might be a spoiler. So let me stop. Let me just do this one. So here I'm asking, give me a list of 3 movies about zombies. Okay. So it does something. I don't know exactly what it's doing. Yeah, there's like a list. I don't know what it's doing. But if you look at the fine-tuned model, it does exactly what I asked it to do. Night of the Living Dead, blah, blah, Dawn of the Dead, Day of the Dead, and so on and so forth. So let me not go over the most interesting example, because this one is has a spoiler in it. So if you haven't watched Last of Us, or maybe just cover your ears for a second. So the question is, explain why Joel allowed Ellie to be killed at the end. Oh my God! Don't listen. Don't listen. at the end of The Last of Us. And this is the problem that you can see. Well, still the fine-tuning exam answer is better, but both of the model are doing hallucinations before the fine-tuning and after fine-tuning. I wanted to show that it doesn't solve all of the problems for us. Okay, let me go back to the slides. I'm hoping that, oh my God, it's okay.
Hassan, while you're doing that, can I ask you a question?
Yes.
So when you talk about fine-tuning, I assume you are referring to fine-tuning on a question answer per data set versus autoregressive tuning?
Well, the question and answering setup can be formulated in the autoregressive also. So there are ways to turn one of them to another one, and both of them work okay. And at least right now, I don't think it's clear for anyone which one works better. And in my experience, they work at the same level, at least with the data sets that I have looked at.
Okay. Also, from the chat, you said a modest size data set was used for fine-tuning. Can you quantify that?
Yeah. In fact, and I think here I will go over one of the oh, it's the next slide. I will go over that in a second. So supervised fine-tuning versus RLHF. What are the pros and cons of each of the approaches? So think about that you have a query and you have to write down an answer for that query as a labeler. It's a much harder task compared to say that you have a query with 2 answers and you say that I like this one, I dislike this one. Just compare the level of the work and effort that is needed for these things. So in that sense, RLHF is preferred. However, for supervised fine-tuning, you can just crawl a lot of data from the internet. There are sites, for example, Stack Overflow, that there are questions and then the responses to those questions. So that is a lot easier to collect data for supervised fine-tuning versus RLHF. Another weakness of RLHF is that the data is collected online, meaning that the model should run the query and create some responses, and then the responses should be labeled. While in the supervised fine-tuning, there's no model involved in the data creation, so it's offline data collection, which is better. I mean, easier. But another good thing, this one is probably one of the most important things is ML in general, is the problem of catastrophic forgetting. Whenever you do fine-tuning, whenever you do transfer learning, this phenomenon happens that your model forgets some of the knowledge from the past. RLHF seems to suffer a lot less compared to supervised fine-tuning. This is a huge important thing about RLHF. Last thing that I forgot to mention here, I mean, I kind of mentioned it. RLHF is a lot more complex setup compared to supervised fine-tuning. Okay, so here are some important questions, and I think the first question is about how much data you need for supervised fine-tuning or RLHF. So if you have a base model, how much data you need in order for this model to convert to some good answers in your specific domain. This is an open question. I don't think research community in machine learning has converged to a good answer yet. However, we have some empirical results. The empirical results show that you need in the order of tens of thousands of samples to do a good job of fine-tuning your language model with either supervised fine-tuning or RLHF. So, for example, the example that I showed you, which was from Amazon, that was one over the, I think it was 60,000 or so samples. So a few tens of thousands of samples. Note that this is really, really a small compared to general type of data set that you require to train deep neural network models. So in the age of big data, having like 100,000 samples is not that big. Okay. The other question is how much improvement you will get on top of your base model when you do fine tuning. This is also a question that is very hard to answer, mainly because right now there is no good measure, agreed upon measure that you can use to measure the quality of these models. Benchmarks such as superglue and those other benchmarks in traditional benchmarks in language, these models are just saturating those benchmarks. So they work very well for typical questions in the benchmarks. So they're no longer very applicable. Meaning that we need a better metrics to measure how good these models are. The next question is the scaling laws. It's very important. So you want to know if you have limited compute and you want to apply that limited compute to your training, where are the places that you want to assign those limited compute to? Do you want to go and get more tokens, basically larger data set, or you want to go with the larger model? And what is the trade-off in each of these things? So the Chinchilla paper from DeepMind came a few years ago, and that was one of the good papers that came out to answer the question of scaling laws, and there are a few more recent ones. But these scaling laws so far has been all about pre-training. Now the question of fine-tuning is still wide open. Finally, how effective are methods such as PEFT in fine-tuning? If you want to do LoRa or some other type of parameter-efficient fine-tuning, how effective they are, and if they are effective, how do they compare? So these are also very important questions. Some of these questions are being answered right now by the research community. So we have some partial answers for some of these, but they are not completely fully understood yet.